on a input string. What then? Well, we need to, we've got a problem there. So we need to do something that, see, if this thing is looping on that, then it's not accepting or rejecting, right? So we want our simulation to reject if this is looping on that. Because this normal Turing machine, it should accept if this accepts that. Well, if it's looping, looping is not accepting, looping is not rejecting. Okay, so if it's not accepting, if it's looping, then it's not accepting. So if somehow we can detect by our simulating Turing machine, if using that simulating Turing machine, if somehow we can detect that this LBA here is looping on this, then we want our simulating Turing machine, infinite tape Turing machine, to reject. Okay. So how to do that? So we need somehow to be able to detect that the LBA, machine M, is looping. Okay. So how to do that? So that's what the proof now boils down to. How do you go about detecting that your LBA M, big M, is looping on the input of W? How to do that? Well, psychologically, you're already primed, right? Obviously, we're going to use the lemma. So now here's like the second core idea. Now we know for an LBA whose finite length tape is little n with G different symbols, we know the maximum number of different configurations that that LBA can have is QNGVN. Right? We know that. Right? So here's quite a nifty idea. Run the simulation for this many steps. Are you smiling? Are you saying, "Oh, nice"? Can you see where this argument is going? I mean, I must say it's much nicer when the argument clicks than occasionally when it doesn't. Then I get really frustrated. But yeah, this one definitely clicked. Okay, so if you run the simulation, so you're simulating ordinary Turing machine is behaving, simulating, behaving like an LBA, and you're going to run it for this many steps. Why? Why do that? What's the point? Well, say you run it for this many steps, and your simulation has not stopped, has not halted. What does that mean? What does that mean? Well, if you run it for this many steps, what happens the following step? Well, then it has to go back to the following configuration. After this many steps, the next step, the configuration of that next step must be one of these. Can you see that? And therefore you've got a configuration that's repeated. Has to be. Because that's the maximum number of configurations that there are for that LBA. Okay? So if you go one more step, you have to get a repeat configuration. Now, since we're talking deterministic Turing machine, then if you just let it run, it'll just go into an infinite loop. It'll just keep cycling. It'll keep looping, right? Because it'll go, it'll get into a repeat configuration, and then it just goes through all the same steps as it did the first time, the first loop, and so on. It'll just keep looping, right? So in other words, oh, the flu, hopefully almost over. So in other words, we have here now a means to detect whether the LBA is looping or not. Right? So all you do is just let it run this many steps, and if it has not halted before then you know it's looping. Okay? That's critical what I just said. So if you know it's looping by doing this test, letting it run this many steps, if you know it's looping, then have the simulating ordinary Turing machine reject. Okay? So now you have a means to close this loophole of what happens when the LBA is looping on W. Well, now we have a means to check. We know when it's looping. Now, if it's looping, it's not accepting, right? And okay, so let's see. I think I've said all this. All right. So now we can said all that. Now let's go to the formal proof, the actual detailed proof. So the algorithm, or Turing machine, same thing. Turing machine is what an algorithm is what a Turing machine does. Okay. So the algorithm that decides this language is the following. So okay. So as usual, you start with a description of your input type. Well, it'll just be a member of your language. So usual ordered pair. So encoded information about this machine M, but the M is an LBA this time. Okay, and W just your usual string. Right. Now the various stages numbered 1 and 2. I think you can. You probably got the first line okay. I don't know if you can see the second. I'll read it out anyway. Right, so here's the actual algorithm. The simulating Turing machine. Okay, so stage 1, you're simulating your LBA. That's what this M is here. Given an input string W. Now it could be any LBA, any string. Right? This ordered pair is just any combination of these two. Right, so you just simulate it for this many steps. Right? It may halt. It may halt before this many steps. Okay, so it's an or. Okay, so either you let it run for this many steps, or until it halts. Okay, one way or the other. Now stage 2 is now if M did halt, then so that means the M either accepted or rejected on W. So if M did halt, then have your simulator accept if M accepted. In other words, if your LBA accepted, and have your simulator reject if M rejected. Okay. Now also, now if M did not halt, so it ran through all of these QN, G to the N steps. So if M did not halt, well, also reject. Okay, and that's the proof. Now there's a bit of commentary after that. Yeah, I'll just wait till the next session. Ciao.